until the end of July. And so today, where he is going to give this coffee meeting talk, and in addition, from 2 p.m., he's going to give a seminar from the third floor, the seminar room. The title is something related to quantum gravity, which may be different from the ordinary effective field theory. So that must be also very attractive, and I hope, so many of you come to his seminar too. Okay, so listen, please start.
Okay, 15 minutes?
Yes.
Okay, thank you. So I'm very happy to be here. So I want to tell you something I'm working on. So this is actually started like 10 years ago. This is a joint work with quantum field theorists and computer scientists. These people are computer scientists. And he's the person. And so there we actually classified what's called the holographic entanglement entropy inequalities, which I will talk about. And since then, so in this paper in particular, we proved that for each given number of parties, the number of inequalities are finite. And so I've been trying to sort of classify them. And then, but we ran out of idea in human brains. So now I'm working with my students to try to use reinforcement learning to classify entanglement entropy. So let me introduce notation. So when I write A, B, C's, these are parties in the sense of entropy. So these are subsystems that you're considering. And so when you have a combination of two parties, I often write it as A times B just to save notations. And then SA is an entanglement entropy. Entanglement entropy between A and its conflict. Okay, so that's the notation. Okay, so those quantities, entanglement entropy satisfies lots of interesting inequalities, and that plays a very important part in understanding information theory and its application. So classically, there is Shannon entropy. And this is a very important point. Of course, Shannon introduced the idea of entropy. He didn't know this was entropy. I think von Neumann told him that it's actually the same as entropy. That he tried to explain how, kind of quantify how much information can transmit it in the information processing. And so this quantifies the symbolic performance for information processing tasks. And but it was shown around 2007 that the number of inequalities is infinite for the party greater than 3. Okay, so the Shannon entropy have infinitely many inequalities. Okay, so quantumly, so this is a von Neumann entropy. So actually, in this case, totality of independent entanglement entropy inequalities is not known. But no one played a very important role. So for example, there is a strong subadditivity, which hold this one. And this was a very important discovery by Leibs, Elliott Leibs, and Ruskay. So this is around 1973. So this is called strong subadditivity, often shortened as SSA. And but in general, actually, it is expected. So there are some. So here it has been proven that there are infinitely many inequalities. Quantumly, it's not known, but numerical evidence suggests that there are infinitely many of them. So it's very interesting that in my work 10 years ago, we found that in the case of holographic system where ADS CFT works, and you can calculate entanglement entropy in conformability theory using weakly coupled gravity theory. So for these particular types of quantum system, we have proven that actually number of inequalities is actually finite for each number of parties. So I will explain you how we proved it, give you an idea. And moreover, in this paper, actually, we have been able to classify all of them up to 4 parties. And for the last 10 years, several other people try to actually classify these inequality for. By now, actually, we know all the inequality up to 5 parties. But classifying entropy inequality for 6 parties turned out to be very difficult. And so we are going to use machine learning to classify. So that's the idea. Okay. And so if you use holography, then actually entropy inequality has a nice geometrical interpretation, such as in terms of triangle inequality. So I would like to explain that. So, so the idea is to use the Ryu-Takayanagi formula. So you might have heard. So I don't have time in 15 minutes to explain what LDH-CFT correspondence, but I hope some of you have heard about it. So you have, when you have a conformal field theory on sphere, then LDH-CFT correspondence says that for some class of CFT, there is a gravitational dual that you can use Einstein gravity to describe the same thing. So if you have a region, sub-region in conformal field theory, what Ryu and Takayanagi showed was that you can actually consider a minimum surface subtending on the boundary of this region, A. And then you can calculate the area of this region. And so that gives you entanglement entropy for SA. So basically, SA is 4 times G Newton dividing the area of this region. Okay. So this is the real Takayanagi formula. So so what you do is that suppose you have n parties, then you can consider 2 to the n minus 1 different entanglement entropy. Because when you calculate entanglement entropy, you consider combination of these subregions, and then you can ask whether a particular region is in or out. So you have 2 to the n. So you have 2 to the n dimensional space. And then entropy inequality is a question of which subspace that it is realized in terms of the entanglement entropy. So you consider the 2 to the n minus 1 dimensional Euclidean space, and you try to specify subspace in which these are realized as entanglement. Okay, so first thing we showed in my paper with 15 years ago is actually that this space of entropy is realized in this way is actually a cone in 2 to the n minus 1 dimensional space. The cone. So namely that, so suppose you have some Euclidean space, say in this direction you have SA, and in this direction you have SA, B, etc. And in general, you have 2 to the n minus 1 dimensional subspace, and it's actually a cone. And then all possible entropies are realized in the inside of the cone. Okay, so it's easy to argue why this is. So first of all, suppose you have a point in this space which can be realized in an entanglement. Then, for example, you can rescale the metric over here. So then, because it's an area, so the entropy would be rescaled. So that means that from that you can clearly see that it is a linear space. And you can also add, so namely that suppose you have one system which realizes particular conformal field theory, which realizes particular point in this cone. Then you can also have another system which realizes another point on this cone. Then you can actually consider just tensor products of these two conformal field theory. And then the entropy would add up. So that means that the space of all possible entropy realized in this way should be actually a linear space. And so therefore it's a cone. And in fact, it's a convex cone. So I should have written convex cone. Because you can add them. Okay, so this is interesting because then the finding the task of inequality is the same as finding all the facets of this entropy cone. Okay, so that's the first step. And the next thing we did in this paper is that we proved that actually this entropy cone, holographic entropy cone, excuse me, entropy cone is rational polyhedron. Okay, so it actually not only it's a cone, but it's a rational polyhedron. So namely that there are only finite number of independent entropy inequalities, which is in contrast to this general quantum case. Okay, so how do we prove this? Well, so you have this subregion. So you can have A, and you can have B, and you can have say C, and then there are some complement regions. And then according to mu Takayama formula, you consider these subspaces like this. And then, so for example, if you have, you can consider various inclusion and exclusion. So for example, if you want to calculate entanglement entropy for A, you consider this minimum surface. If you want to calculate entanglement entropy for B, you consider minimum surface. If you consider entanglement entropy for A union B, you consider this region, etc. So then what you can do is you consider dual of this configuration, namely that can you see blue? So you consider each of these regions by taking the dual of this in terms of vertex, like that, and then you connect them like this. For each minimum surface, you connect them. Okay, so then what you can easily see that for each edge, you can assign the area of the corresponding regions. Okay? So therefore, in this way, you can have a graph model. You can have this kind of discrete geometry. You can have a graph model. To calculate entanglement entropy. Okay? And so rather than calculating, considering complicated bulk geometry, we can consider this kind of graph model. And so each of these blue line correspond to Ryu Takayama, a segment of Ryu Takayama surface separating these regions. So then what we're going to do is to consider what we call the minimum cut. So namely that, so if you are, for example, interested in some boundary region, which can have A1, AI1, A1, I2, etc. So suppose you have some kind of region, then what you're going to do is to consider a minimum cut. Separating A and A bar by considering combination of these vertices. And so then discrete entropy is given by minimizing all these possibilities. Okay? So conversely, you can also show that you can actually prove. So this requires some proof that so I have shown you that for each configuration, for each geometry in the bulk, you can construct a graph. But you can also prove, and this requires some knowledge of hyperbolic geometry, that for each graph, you can actually reconstruct the hyperbolic geometry in the bulk. And then for each given time, so then it becomes a finite problem. Because for each number of parties, you have a graph of finite number of vertices, and then it's just a minimization program. So then it's clear that the corresponding constraint should be finite. So that from this, you can actually prove that holographic entropy cone is rational polyhedron. Okay, so that's the idea. So in practice, then what we're going to do is, in practice, what we're going to do is the following. So we try to find, since this is a finite dimensional, so we try to find inequality in a finite process. And so even though, however, the number of independent inequalities is finite, it may be computationally heavy to perform them, to search for them in brute force. So what we're going to do is that in practice, we guess inequalities and check whether they are true inequality or not by constructing the corresponding geometry. And but then, since we're guessing the inequality, you can ask, well, how do we know that we have found all the inequality? How do we know we have found all the inequality? So have we found everything? So we have an answer to that, which is that we can actually, if we can construct extremal arrays, if you can construct extremal arrays, then we have done the task. So namely that the following we have the, so since we are considering this discrete geometry, we have the following concept. So there is a thing called the extremal array. These are the rays in this convex cone that cannot be written as a proper convex combination of other elements in this cone. So what in practice we're going to do is that suppose we have a candidate for the holographic entropy cone. Then what we're going to do is that we can calculate all the extremal rays defined in this way. And for each ray, we try to find the bulk geometry. Namely, in practice, what we're going to do is to try to construct this kind of graph. And then if we can construct the graph which realizes the extremal rays, and then we can do that for each extremal ray, then we are done. Okay, so that's, and then we have classified all the entropy inequality. So that's one thing. Another thing we need to double check on that is to see whether given entropies inequalities hold for all the physical systems satisfying the holographic construction. So namely that, how do we prove that it holds for all holographic states? So let's see, how am I doing time? Do I have like 5 more minutes or so?
Yes.
Okay, good. So there's actually, so this was the most difficult question we faced. And then we actually came up with a very efficient method called proof by contraction. So let me see if I can explain this. So suppose, let's say the strong subadditivity. So strong subadditivity inequality is like this: SAB plus SBC is greater than or equal to SB plus SABC. So this actually not only for holographic system, but for any quantum polynomial entropy. This was proven by Lee and Sky. And so for this, I introduced the following notation. So you have X and Y. So you have the following things, and I define SA, XA to be a 2-dimensional vector 0, 1, and YA is equal to 0, 1. Okay, what do I mean by this is that here A is included in the first entry and not included in the second entry. Right? And here A is not included in the first entry and A is included in the second entry. So I define a 2-dimensional vector in this way. YB is equal to 1, 1, etc. So I define this vector, and then what we see is that with this notation, this can be written as SAI alpha I is equal to or greater than R of S AR, beta R. And so what we can, so the proof like construction is the following things. That this inequality of this type is a valid holographic entropy. So this is a valid one. If and only if, so you can actually prove this by repeatedly doing triangle inequalities. But you can prove this provided that if there is such a map F, which maps 0, 1 to L to 0, 1 to R, such that x minus f prime measured in the metric on the left-hand side is greater than the image. Okay, so the detail is a little bit complicated, but we can actually prove that once you find an inequality, we can check whether all the inequalities are satisfied, and all the holographic states satisfy this. So this sort of completes the task, and so in principle, this is a finite task. Okay, so we actually carried out this task for 3 parties, 4 parties, and then the subsequent paper actually classified for all the entropy inequality for 5 parties. So in this way, this framework successfully classified holographic entropy inequalities for up to 5 parties. But however, it faced fundamental challenges in going to higher number of parties. For example, if you want to do it for 6 parties, we have to actually do this for 63-dimensional space. And the contraction method can easily prove the validity of individual inequalities, but confirming that search is exhaustive and complete in such a high dimensional space is challenging. So what I did was first to send one of my graduate students for an AI company in San Francisco and have him trained for a quarter and brought him back, and then we started working on it. And so to overcome this challenge of completeness verification, what we did was that we developed a reinforcement learning approach. So our reinforcement learning agents are trained to determine if target entropy satisfies the holographic constraint by learning to construct the corresponding quantum gravity computation. Namely, what we trained the AI so that for given entropy vector, so for any entropy vector, the machine tries to reconstruct the quantum gravity geometry in terms of graph mode. Okay, so that's actually we can easily train machine to do that. And of course, it's not machine cannot always construct it, because the thing is that if the target entropy is inside of the correct entropy cone, then you can actually construct the correct geometry precisely. So this is how machine learns it. But if the target entropy is outside of the cone, by definition, there is no geometry. There is no graph model. So machine should not be able to construct it, but machine learns how to do it. So try to do as best as you can. So then there is an error. So basically what we did is to use that error as a reward function and try to actually minimize that function. Okay, so basically, if the configuration is found, it means the target entropy satisfies the constraint, and so that the reward function is maximum. And but if no valid configuration exists because target entropy lies outside of the constraint, our optimized reward function provides a continuous landscape that measures the proximity to the boundary to saturate entropy inequality. So basically, since we have the reward function, once you are outside, the machine can see how you can go inside of the cone. So this allows us to compute a local gradient that guides the machine to go toward the genuine boundaries. And so this approach offers this systematic method to complete the verification of entropy inequalities for large number of parties. So as a proof of principle, actually, we have successfully demonstrated that this framework is able to identify all the holographic entropy inequality up to 3 parties. And then we went out to apply that for 6 parties, and that's what we are working on. And we have already found the new inequalities. there are, for 6 parties, there are many unknown inequalities. And in fact, machines have been able to actually identify the true inequalities that were not known. And so I think this demonstrates that the feasibility and usefulness of our reinforced learning framework in high-dimensional entropy space. So our immediate goal is to classify all the holographic entropy inequality for 6 parties by doing this in terms of machine learning. And I hope so. Actually, the entropy inequality that are satisfied only on the holographic system actually gave very important insight into quantum gravity. For example, for 3 parties, there is a thing called the monogamy of mutual information. That were actually very important in identifying the fireball paradox in black hole. But ultimately, we aim to achieve complete classification of all number of parties using this method. Okay, so thank you. That's all I wanted to say.
Thank you very much. So as usual, so questions from non-experts. Any questions are welcome. Yes.
Ask 2 questions. So in the holographic case, you asked to say that there is a noise, the entropies are not infinite, unequal. So is there any upper bound of the?
Yeah. Well, it's not the upper bound because it's you have the well. Yeah, so let me see. So upper bound on all possible entropy, right? Let me see. So let me see if I can answer that question quantitatively. So I can prove that there is basically that if you can actually do the combinatorics of the graph, I should be able to. I don't have a new quantitative answer to your question, but because the reasoning is that because we have this finite for each number of parties, you have a finite graph with finite number of vertices. And so that's sort of, so in principle, one should be able to answer your question. I think we might have put that formula in our paper, but I don't have it also. There is a formula. One can find a formula.
Okay.
Yeah.
And second question is that for your training machine, do you give an input of this purity of the state, like is it whether I am considering a mixed state or is it?
This is actually totally discrete geometrical question. Namely that, so for each graph, you can calculate all the entropy vectors, right? So what you do is that for given geometry, you can construct a vector. And then if the machine is asked to do the converse. So namely, somebody gives a vector, try to construct the graph model. And then, so we gave them. So basically, machine can actually self-run because you can, once you have this, you can construct this, so. And then they ask machine to identify the pattern.
I see.
And then they try to run that and then reconstruct it. So there's nothing quantum in this construction. The machine is just doing some combinatorial program.
Nice.
But the great thing is that, of course, and as I said, so if you are inside of the cone, you can actually, and the machine is actually very efficient. I'm very impressed because if you are just inside of the cone, then actually the error is almost zero, negligible. So the machine can reconstruct the correct bulk geometry for each given entropy. But then, of course, if you're outside by definition, you cannot have the exact reconstruction. So then there is an error. But as you approach near the facet of the cone, the error becomes smaller and smaller. So then there is a gradient. So you can use a gradient to approach the inside of the cone, and then you can actually determine the shape. That's the idea.
And also this blue curve looks like some tensor network. Is it?
Yeah, it's very similar to the idea of tensor network model, actually. Yeah. I think actually one of them might be author of the co-author of the paper.
So I understand the AI is very effective to classify kind of the discrete model, but
Yeah.
is there any chance of the physics give some kind of constraint to the model of black
Well,
model?
or converse with because for many parties we don't know what kind of new inequalities are there. So machine is supposed to teach us about the new inequalities and entropy as
But then if you know some of the inequality
Yeah.
which machine identifies, then you get some common feature of the model, and then it can go back to the physical.
That's right. Yeah. So this was already happened. So for three parties, as the classically actually only non-trivial inequalities are this Elliott-Leap and Rusaki's strong subadditivity constraint. But in the holographic setups, there is actually a new inequality called the monogamy of mutual information, which are not always satisfied for generic quantum system, but should always be satisfied for holographic system. And it turns out that this taught us about one of the very important puzzle about the black hole system called the firewall paradox. And so it actually gives us some kind of important hint in understanding.
Yes.
There are some examples of holographic data which were outside the context of gravity, for example, condensed matter.
Yeah, so if there are models, so many of the condensed matter programs do not have nice weakly coupled holographic duals. Some may, so there might be some, but for those, this is always satisfied. These inequalities are always satisfied for holographic system, which means that you have a quantum system which has, which can be represented as weakly coupled Einstein gravity, and coupled the finite number of matter fields. So if you deviate from that, of course, this inequality should be modified.
But are there any old examples
Of what?
graphic?
Well, that's not my expertise. So I do not know. Certainly there are people like research there who are very interested in holographic description of quantum system. But I should tell you that many of those models are not quantitatively reproducing exactly the kind of condensed matter quantum system that the condensed matter physicists might be interested in. I think they are more interested in understanding some universality class of such systems. And however, in order to actually apply this idea, this is a sharp question whether certain system are satisfying inequality or not. Inequality is a very sharp quantitative statement. So therefore, it's not obvious whether this holographic system, which belongs to the same universality class as the interesting condensed matter system, satisfies the same inequality. It's a different question.
Yeah, I have to interesting those maybe, but I was simply trying to understand this.
Yeah.
So for example, what would be the corresponding parties in, let's say, about many body systems?
Yeah, so in many body systems, you can consider, for example, if you have some spin system, for example, you can consider a subset of spins, and then you can ask what the entanglement of the subset of the system with the rest of the system. Or you can consider two subsets and what are the entanglement of the two subsets for the vacuum state of this system. You can ask this question. Or you can ask this question even for excited states. This is about the geometry. So you can have excited states also. Then you can ask whether particular excited state has this particular entanglement pattern. And then if such a system has quantitatively good holographic representation, then they should satisfy this. That's all.
Yeah, sorry, maybe I missed something. Can we extend the three body inequality to the four body or five body?
Yeah, so when I say parties, maybe it's the same as what you call bodies. Namely that so these A, B, C, etc. represent subspace of the Hilbert space, right? And then you can ask, so for example, what subfactor of the Hilbert. So suppose, for example, you have a spin system, and so you can consider. So suppose you have n spins. So then these A, B, C, D, etc. may represent each one of these spins. And you can ask entanglement between spins So for example, this is a union of the two spins. For example, these are union of three spins, for example. And then there is always, so this inequality is always satisfied for any quantum system. So you give me any three spin systems, for example, three qubit system, then it's always satisfied for them.
I mean, can we instead this to four qubit systems?
Yeah, that's the project I'm working on. Yeah, that's what I'm working on. So this is what I call fun. So what I did was that I was able to classify all the inequality up to four spins, then four parties. And 5 party has been classified for the last 10 years. And but 6 is more challenging because you see that you can choose. You have even for 3 parties, you have for 3 parties you have actually 5 possibilities, right? Because you have 2 to the 3 minus 1. And but for 6 parties, you have 23 choices of entanglement entropy. So it's a very high dimension. So if you want to specify this rational polyhedron in this 23-dimensional space. So that's the question. So what I'm saying is that the machine learning can help us identify this rational polyhedron. Yes.
Yes, I'm also interested in that inequality. So in the case of four, is it always like the even is on the
Yeah, so there's actually a series of this. So there's actually a sequence of entropy which holds in any numbers, and there is a generalization. So you can, for 4 parties, for example, you have A, B, C, D, C, D. You can choose any 3 of these 4, and this is satisfied.
I hope, is it always like the even number of parties?
No. So I'm saying that it's in general this form. And then this proof by construction validates this. So these are alphas are integers, I think.
Yes.
And these are the sort of union of subsets of parties. So you can always write it in this way, right? So A1 in this case is AB, A2 is BC for example. And then in that case, alpha is 1 for both. You can always write it down. Yes, you have a question.
So for like the generic mixed state is also satisfied in poly.
No, I don't know. This is about pure state.
Oh, this is all about.
Yeah, this is about pure state.
So
I don't know.
Okay.
Yes.
And you said you can't entropy by solving the minimum surface problem.
Well, so this is to represent the minimum surface program to.
I was wondering if there's an interesting interpretation for the maximum flow problem. If it's
Sorry?
maximum flow problem.
What is that?
If you have a minimum cut problem from a graph, then if the strong duality force and the solution is set for maximum flow between.
Maximum flow. Oh, yeah. So there is a different presentation of the same thing.
And have a different interpretation.
I don't know, but so there are actually people like Matt Hendrick to try to actually reinterpret this this construction in terms of such a picture. I do not know whether this has been useful.
Any further questions from online participants?
Can I ask one question?
Yep.
Could you? Yeah. Sorry for I couldn't attend in person. So I'd like to know the flavor with the new equality you found in for the 6 parties.
Okay. Well, it's for 6 party. Yeah. So okay. So I should bring it. It's complicated. It's complicated. I don't remember the precise form. But it's So maybe I should try to understand the physical interpretation of that also. Yeah. So I know this just very recent. So actually, So we have not started to understand its physical implication. Sorry, I should have written this. Yeah. I'm sorry, I didn't prepare.
Thanks so much.
So the question is alpha and beta small integers or?
Oh yeah, that's a very good question. So what kind of integer appears here? These are positive, non-negative integers. And yeah, so I don't know. Yeah, so these are interesting questions. And this actually helps us because the machine learning process is sort of a little bit, there's a fuzziness to it. Because reward function, we cannot calculate precisely. The machine learns this and then try to reconstruct the geometric space. And the reward function gives you the measure of the failure. But if you just use that, then the surface of this cone is fuzzy. So then at some point, I have this idea that, well, these are all integers. So that means that if you come close enough, then you can just actually determine the first very sharply. Because you can just ask for the closest integer that you can have. Yeah, so this is actually very important to the integer.
And so it's, for example, for fixed parties, so the integer is not so large.
No, they are not large. They are not very large. Fortunately, they are not large. Yes. If they are very large, then eventually it becomes not easy to actually sharply determine, because then essentially these are rational numbers.
Any other questions? That's okay. Okay, so thank you very much.
Well, thank you for your attention.
Obrita is going to give additional